For the invitation to speak. Okay, so I'm going to talk about the title. What's in the title? So I'm going to talk about a theorem which provides. There's a couple of different ways you can look at it. One way is that it provides a quantitative sufficient condition for an annulus diffeomorphism and a symplectomorphism to have periodic points. And the other way you can look at it is that the conclusion, it's not just existence, it's also quantitative. So it tells you a little bit about the geometry of the diffeomorphism near the periodic points. Okay, so we're going to start with the theorem of Frank's. And there's a number of papers about this theorem, but the specific case that I'm going to be talking about was in a 92 paper. So if a diffeomorphism psi of the annulus is area preserving, and the closed annulus. And it has any periodic points. So these are points which return to themselves under a finite iteration of the map C. If it has any periodic points, then it has then it's going to have infinitely many interior periodic points. So this theorem sets up a dichotomy between between different types of annulus diffeomorphism. So there's either the ones which have, they're very interesting. They have no periodic points, and the ones which have infinitely many. So I guess both have interesting dynamics, but in different ways. So one thing I think to notice is, or maybe the first question to ask is, okay, so the first thing to notice is that this is a 0 or infinity dichotomy for counts of orbits. And the area preserving condition is crucial. So there's very simple counterexamples you can write down. One of them is even in Macduff-Salomon, which satisfy all the other hypotheses of this theorem, and also all the other hypotheses of the Poincare-Berkoff theorem, if you're familiar with that theorem, and yet have no interior periodic points. So the area preserving condition is crucial, and it's also, so in this dimension, that's just sort of the condition that this map is symplectomorphism, and that's a common theme in symplectic dynamics in higher dimensions as well. This sort of dichotomy between periodic orbits, between counts of periodic orbits. So that motivates us to sort of study these diffeomorphisms using area preserving as an assumption, and therefore we can use quantitative tools. Okay, so let's set some notation. So I'm going to consider the annulus parameterized as the interval from -1 to 1 using the coordinate x crossed r mod 2 pi z using the coordinate y. And I'm going to fix the area form omega and a one form beta, which is a primitive of omega. This choice of one form can be weakened, but for now, just think about that one. And I'm going to consider pairs psi y plus, where psi is an area-preserving diffeomorphism, so a symplectomorphism. And psi fixes the boundary components each. So there's the set x equals plus and minus 1. It fixes both of those. And it's orientation preserving because it preserves omega. And also, so in some choice of lift, psi tilde to the universal cover of the annulus, we have this rotation condition. So psi is a rotation by y plus near x equals plus 1 and by y minus near x equals minus 1. Notice that the choice of y plus, y minus, and the lift are all equivalent. So we're really, so that's why the choice of y plus identifies what diffeomorphism we're talking about. So what we need to consider are symplectomorphisms, which are pure rotations right near the boundary. Okay, so I promised you some quantitative tools with which to study psi. So the main quantitative tool I'm going to use is called the action function. So notice this one form is closed. And also so just based on the cohomology of the annulus, this one form is going to be completely determined by its value on any generator of h lower 1. H1 class is determined by the value on and because psi is a rotation near the boundary, this suffices to show, so its value is going to be 0, and so we get that this one form is exact for some function f. So I guess I'll just write is exact here. So we can define So we can define this function called the action function determined by these two conditions. And f is going to tell us a lot about the dynamics of psi. It's going to be our main tool to study psi. So from here, we can immediately compute the value of the action function on the other boundary. So this is going to be the omega tilde, so some lift of omega to a tilde, the omega tilde area and a tilde between okay, so it's going to, I guess that would be the lift of y, but so this is going to be the omega area in a tilde between y equals 0 and its image under psi tilde. So this by sort of abusive notation, I'm calling this f the flux of psi. So essentially, if psi is not too complicated, so if this is the curve y equals 0, and this is psi of y equals 0, then f is going to be this area. So it's fairly straightforward to compute that f at negative 1y is minus y minus plus f. So I guess a couple of things to notice. So one is that because psi is a rotation near the boundary rotation numbers should, no, because psi is a rotation near the boundary, this is going to be, f is going to be constant near the boundary. So notice I said for any y, this is true. And then also, this function is interesting already because it's recovering the boundary rotation numbers. So it's telling us something about psi. OK. So I also said that at the beginning that I was going to talk about some theorem that would tell you about the geometry of your diffeomorphism that you started with. So the action function recovers the geometry in an interesting way. So if I have some fixed point, and I take some curve, let's call it eta, between that fixed point and the outer boundary. So in general, the situation could be a lot more complicated. But in the simple situation, when this curve does not cross this curve at all, so this curve is psi of eta, then there's some area here. So the green area is going to equal f at xy plus some integer that's essentially determined by the choice of y plus. So that's how f knows about the geometry of the diffeomorphism I started with. OK, so how are we going to use, OK, so this is what it does, but how are we going to use it? So a periodic orbit is a finite set of points in a finite list where psi sends the ith element of the list to the ith plus first mod L, which is the cardinality of the orbit. And it has, once I have a periodic orbit, it has a total action, which I'm going to denote by curly A. And that's defined as the total the sum of all the values of the action function at points in the orbit. It also has a period, so I'm going to denote that by L of gamma, and that's just the cardinality of gamma as a set. So in this case, this would just be little l. OK, so then together, these determine some number called the mean action. So each periodic orbit has a mean action. Why would I be interested in this number? So one thing you can check if you go through the definitions is that when I take a cover of an orbit, so for example, say I just took this orbit and then stacked another L tuple next to it, that doesn't change the value of the mean action, right? So both of those orbits have the same mean action value. So if you know the distribution of mean action values, you have a lower bound on the number of different periodic orbits. So that's one reason to be interested in this. OK. So we averaged the action function over orbits. And so what I'm going to do is relate the average of the action function over finite orbits to the average of the action function over the whole annulus. And yeah, so I'll explain what I mean by that. And then we'll come back to sort of the thing I said at the beginning, which is that this should give you a quantitative sufficient condition for periodic orbits. So oh, sorry. So I'm trying to remember to put the y plus everywhere. So the action function depends clearly on psi and y plus. And then you can show that this doesn't depend on the choice of beta. And what I'm going to define here also doesn't depend on the choice of beta, but I'm just sort of saying that to just remind you that f, even though psi and y plus aren't in the notation, it does depend on them. So the Colombian variant of the pair psi and y plus is defined as the average value of the action function over the whole annulus. And sorry, so w, or an omega. And then just to, this 2 is going to show up again later. So this number is just 2. So that's where you get this value for the Colombian variant. Okay, so you should think of the Colombian variant as a generalized rotation number. I believe Igor wrote a paper about that. So it's so it's if you compute using that beta, the Colombian variant of just a rigid rotation, you're going to just get the rotation number back. So I think we'll need more space. Okay. Oh, and you wrote another. Yeah. Okay. So I'm just taking objects that I've introduced, so psi, y plus, y minus, and f, be as above, and assume that the Colombian variant of the pair psi, y plus is less than the max of the 2 boundary values of the action. Or one of the 2 boundary values of the action is rational. This is kind of a side case that just has to do with that assumption. So the main theorem is assumes this. Then the infimum over all the mean action values of periodic orbits is less than or equal to the Colombian variant. So to unpack this, that means that for all epsilon greater than 0, there is a periodic orbit of psi which has mean action less than the Calabi plus epsilon. So I guess so circling back to what I said at the beginning, we have a quantitative condition. So this is something you can just compute. You can compute this in some cases when you have a really strange symplectomorphism. So maybe some odd composition of things, something that's not anything close to being Hamiltonian or something like that. I mean, yeah. So you can compute this, and then even in cases when psi is hard to understand on the nose, and then you get periodic orbits. So that's sort of the way that this theorem quantifies the search for periodic orbits. Then there's another thing that I should take some time to write down. Oh, I guess, yeah, I'll want that up there for to refer to. So if you replace the pair psi y plus with psi inverse minus y plus, then the assumption, then we get a statement that's kind of like Calabi greater than the min of the 2 boundary values of the action, then the sup is greater than Calabi. Okay, so perhaps we can just forget about the quantitative part of the conclusion and then just say there exists an orbit, a periodic orbit. Okay, so together with the theorem, this corollary that you obtain immediately by swapping these 2 out tells you that unless, so the minimum of these 2 numbers equal to the Calabi is equal to the max, their psi has periodic orbits. So it was pointed out to me by Saban Seyfedini that this means that if you have a pseudorotation, so something without, so that falls on the 0 side of this dichotomy, then you must have this condition. I guess that's sort of what I said, but just backwards. I hadn't thought of it that way. So this is, so there are, of course, examples where this thing that I underlined in blue holds, and where you have plenty of interior periodic points, so any rational rotation, for example. But you sort of must have this condition to fall on the 0 side of this dichotomy, which is, so it sort of gives you a quantitative way to see how, I mean, it's not really like a measure or anything, but it's sort of like having all these things be equal is maybe less common, or it's maybe more delicate than having them be different, in which case you are definitely on the infinity side. Oh, and please stop me if you have any questions, ever.
Are there some results where you can actually estimate the action of the fixed point? So where L of gamma is 1.
You know,
some results.
I would love that, but so yeah. So the way that this theorem is proved is using, I'll hopefully get to that, but it uses an asymptotic result on the filtration of ECH by, so embedded contact homology by symplectic action. And so you, I mean, so you have to look in high index. So then high ECH index is generally going to correspond to high period. Yeah, I mean, if you could characterize which, yeah, I mean.
Perturbativity, yes. I mean, not so far from my gas or something.
Yeah, maybe.
Can make such estimates, but in general, that's really hard.
Yeah, I mean, if I think I were trying to say something about all psi, then I don't think I could do anything. Okay, so yeah.
Do you have an example where you had strict inequality? Will the
oh yeah. Yeah, so I can give you some examples. So there's this, there's the, what did I just say, rigid rotations. So they're of this, well, did I erase it? Yeah, I did. They're a rotation everywhere. So rigid rotations don't satisfy the hypotheses. And they either have, so if the rotation is rational, then you get infinity periodic points. Periodic orbits all have mean action, which is equal to the Calabi, which is equal to the min, which is equal to the max. If it's irrational, you still get Calabi equal to the min, equal to the max, but there's no periodic orbits, so this infimum is equal to plus infinity. Okay, so these are sort of the bad cases. Maybe the best case you could imagine are, I think most twist maps are going to be like this. So let's just take a very simple example. So this curve, I think this is going to be a negative Dane twist. So I should turn left. So the image under this map of this this yellow curve is the white curve. And for this one, the boundary values of the action are all 1/2. The Calabi is 1/3. And the infimum of mean action values is 1/4. This map actually isn't a rotation at the boundary or near the boundary. It is at the boundary, but I see one close to things which are, and so you can, basically you get.
So here you can write that explicitly, right? I mean, in
Yeah,
general.
yeah. In general, you can't. Sometimes you can bound it though, which is maybe all you need to get the yellow assumption in the theorem. Yeah.
So can I rephrase my question? So how to think about the equality case of this?
Oh, it should morally be either rigid rational rotation or a pseudo rotation. So something that has something that's over here. So morally, the way you can think about it is sort of maybe. I hesitate to say most because there isn't a measure on this space or anything that I'm talking about, but this is the equality case. This should be the strict inequality case, but that's that's not on the nose true because this has infinitely many orbits, but it also has equality. Yeah.
It could be true that equality is exactly if and only if it's a rotation or a
Pseudo rotation. Yeah, it could be true that pseudo rotations and these are the only ones with equality. Yeah. Yeah, and then so the way to come up with examples of maps for which it's hard to analyze the dynamics directly, but which it's easy to compute that inequality is if you take an irrational rigid rotation and then compose it with just any Hamiltonian, not any Hamiltonian, but many Hamiltonians, you can get that inequality fairly easily without understanding anything about the map. So yeah, I can. But it's maybe hard to compute the action function directly, but you can at least get that, or completely, but you can at least get the inequality. Okay, so Hutchings also. So Hutchings has proved an analogous theorem for the disk. So if you just rewrite everything exactly the way that you would think to, so instead of having the maximum of 2 boundary values of the action, there's only 1. But so there's 2 things to say about this. So one is that the obvious So there's an obvious way to prove the annulus case from the disk case, and that would just be to take the minimum of those 2 numbers and collapse that boundary to a point, and then you get a disk, and you should satisfy the analogous hypothesis. But that doesn't work in general. So there's a whole appendix to my paper where I show this. And then the second thing to notice is maybe an explanation for why this is true. So So this theorem, so the disk theorem can still, so I guess if the hypotheses apply to the disk theorem, then you could still be on the finite side. So if the hypotheses in the disk theorem apply, then you can still just have one fixed point and be, so Franks' theorem applies to genus, I mean, in general, it says something about genus 0 surfaces. So on the disk, the dichotomy is 1 or infinity. And so if the hypotheses apply to the disk theorem, then you can still be on the 1 side of the dichotomy. But we just sort of talked about that in the annulus case, if the hypotheses apply, then you are definitely on the infinity side. Okay, so how to prove this theorem, and or why would someone who comes from contact geometry start thinking about these questions? Okay, so the general idea is the following. So first you suspend the annulus as a page of an open book decomposition. So a kind of quote unquote vibration, but not quite, of a lens space. In such a way that it's compatible with the contact geometry. So in such a way that, that the topology of this vibration tells you about a contact form. And then I think, well, contact geometers have invariants which can measure things like action. And mean action. So first I'll tell you something about the first part, and then I'll tell you what exactly I'm using to measure the action and mean action of these orbits. So So I'm going to use Y to denote my closed-oriented 3-manifold, or throughout to denote that. I'm going to denote my contact form by lambda. Its volume is the integral over Y of lambda wedge d lambda. And I'm going to denote the Rabe vector field by R. So and then I'm going to denote my Rabe orbits by gamma. So these are going to be and a Rabe orbit has a symplectic action. So which is the integral of lambda over the orbit. So all of these things are going to match up nicely with the dynamical objects on the annulus side. Yes. Yes. Yeah, so I'll describe that in probably the next board. So this is, an open book decomposition of a 3-manifold Y is a pair B pi. B is an oriented link, and it's called the binding. and pi is a fibration of y minus b over S1. And the preimages of points are the interiors of Seifert surfaces of B. So yeah, so it's a particular type of fibration of the complement of a link, and so sort of the importance of this condition is that these are called the pages. Is that the pages only meet the binding once. So you can have there's plenty of different types of surfaces in and families of surfaces and contact manifolds that can be compatible with the contact form, but I'm picking ones that are arranged in this particular way. So I'm going to say that a contact form is adapted to an open book decomposition if the Rabe vector field is positively transverse to the pages and positively tangent to the binding, and it takes finite time under the Rabe flow for a point which is not in the binding to return to its original page. And this time is called the return. So yeah, we'll do this on another board. So the time it takes for a point to return to its original page is called the return time, and the place where it goes is its image under the return map. And that's how I'm going to define return time and return map. So the return time, is a function. I said this in the wrong order. It's a function from the page to R, and the value that it takes on a point in a page is the time it takes that point to return back to its original page under the Rabe flow. And the return map is a diffeomorphism of the page, and it's given by the image under the flow of point Z for the return time of Z. So I think one way I tried to describe this is that, say you have a bubble in a wand and you're blowing the bubble, and then the bubble goes through a wormhole and wraps around the wand again. That's sort of the idea of what's going on here. Okay, so why did I introduce an open book decomposition and adapted contact forms? Well, there's a way to set up, in what I just erased, there's a way to set up a contact form on a lens space with an adapted open book decomposition so that the return time is the action function and the return map is the diffeomorphism. So let psi, y plus, y minus, f be as above, sort of plus some assumptions. So there's a couple more assumptions, but the main ones are the the action function is positive, and this quantity, which I'm going to call P, which is just the sum of the two values of the action function on the boundary, is an integer. So assume these two things are true, then there's a contact form, and I'm calling it lambda tilde psi on the lens space LPP minus 1, which is like I just said, adapted to an open book decomposition with annulus pages, return time, the action function, and return map the original diffeomorphism I started with. I think I will need a little more space, but I'll do another condition here. So the volume of the lens space with this contact form is equal to twice the Colombian variant. And that just has to do with the 2. Oh, I think I erased it. The 2 that's in the definition of the Colombian variant. And then the last condition is that because the return map is psi and the return time is f, you get a bijection between the periodic orbits of psi and the binding of this open book with the Rabe orbits of your contact form. And the bijection sends total action to symplectic action, and it sends period to intersection number with the page. So, right, so I would say, so this theorem is proved by a direct construction, and I would say so the idea of the theorem was what I had already told you, which is that I should put my annulus in a 3-manifold in such a way that the Rabe dynamics recover, so basically so that this statement number 3 holds. So the Rabe dynamics recover the dynamics of the diffeomorphism. So the real content of the theorem is that the 3-manifold is LPP minus 1, or of the proposition. And this open book decomposition is the standard one that you get from the standard open book decomposition on S3, and then you, with annulus pages, and then you take a quotient by Z mod P to get LPP minus 1. Okay, so otherwise, you construct this manifold by taking a mapping torus of psi, and then you have to collapse the boundary in order to get a closed manifold. And the way in which you have to collapse the boundary in order to get a contact form that extends over, a contact form that satisfies all of these things, forces you to pick LPP minus 1. Okay, so how are we going to get the theorem from this? So basically, we've reduced this whole thing to a statement about contact forms and their Rabe orbits. So we're going to use embedded contact homology. So this is a Floer homology theory, and the generators. So let's just define it for some contact manifold y lambda. So the generators is as a vector space over Z mod 2 are of this form. So I'm going to call them alpha, and they're sets of pairs of where the first part of the pair is an embedded Rabe orbit. The second part of the pair is a positive integer, and the total homology class is 0. So you can generalize this and this, but we don't need to. And the differential counts differential counts J-holomorphic curves in R cross Y of ECH index 1. So by that I mean the differential coefficient of, for example, alpha 1 in alpha 0 is a count of J-holomorphic curves in R cross Y, which limit to alpha 0 at plus infinity and alpha 1 at minus infinity. So, and then it's graded by the ECH index. This is a Z grading if the first Chern class of the kernel of the contact form is 0, or is torsion. But in this case, it's 0, and it has a Z grading. Mm-hmm.
It's about propositions.
Mm-hmm.
Is integer an assumption?
Yeah.
And how do I take receiving or something like that?
So when I'm trying to extend, so what I do is I prove the theorem, or I prove something that's similar to this theorem for these manifolds. And then in order to extend from P to an integer to a rational, you can take a power of psi. And then in order to extend from a rational to a real number, you have to perturb psi. And it you just have to actually like look at the map and integrate things. And yeah, so I wouldn't say there's some idea behind it. I actually thought for a long time about proving this proposition for rational P using rational open book decompositions, but it was really hard. And I think that most of the way that people, or a major method for understanding rational open book decompositions is by changing them to something which has a normal open book decomposition, and so then I messed this whole thing up already. So,
Sorry, what's the rational?
So you can weaken this. Where is it? Yeah, they don't have to be ciphered surfaces, so they just have to the closure of the page just adds B, and so maybe your page wraps around multiple times. So for example, there are rational open book decompositions on these lens spaces whose pages are disks. But there's no, if your lens space isn't S3, then you can't get an open book decomposition with disk pages. Yeah. Are there any other questions? OK, so why are we using ECH? There's sort of two reasons. So the first reason is this theorem of Dan Cristofaro Gardner, Michael Hutchings, and Vinicius Ramos. I think this is 2015. So I'm paraphrasing the theorem. There's a it has slightly, but in this what I'm saying works in this case. So if the first Chern class of your contact structure is torsion, then given a sequence of ECH homology classes, so after you mod out by the differential, sigma sub k with the ECH index of sigma sub k equal to k and going to infinity. then they have representatives. I'll call it alpha sub k. So this is going to be sum of generators. Oh, sorry, has a representative, which is a sum of generators all of which satisfy so I'll call these maybe alpha sub ki or something, which satisfy the following thing. No. For which okay, so this is a bit of a complicated statement. So what I'm saying is that if I'm in this situation where the first string class is torsion, which I am, because I'm in a length space, then if you give me any sequence of ECH homology classes whose indices are going to infinity, then I can represent each of those with a sum of generators. And for all of these, sorry, I use a slightly different version of this in the paper. I think this is not. So there's something called an ECH capacity, which is a slightly different thing, but so if k is large enough, can get this inequality. I'll say that. The limiting argument actually has to do with ECH capacities, which take a little bit more time to define. But so each homology class can be represented by the sum of generators. We're calling them that. And then eventually, if k is large enough, you'll be able to find generators for which this inequality is true. And you will continue to be able to do that. OK, so in order to apply this theorem, I need those homology classes. Otherwise, I'm not going to be able to get any generators. So I computed the ECH of these length spaces, and they have a single, so the 2k homology class is generated by a single generator if k is a positive integer and there's nothing otherwise. So you can take the homology classes in that theorem to just be the generators of these groups. So you're going to get infinitely many indices in which you have a generator of the ECH homology group which satisfies this action inequality. OK, and so what I need is an inequality in terms of for the mean action, which requires me to have another inequality for the period. So I'll just quickly say that we can compute that also for some of these, so for at least one of these alpha k's, I think I said alpha ki, so at least one of the orbit sets representing in the cycle which represents that homology class, we have this this inequality. So intersected with the page is greater than or equal to some then its index times greater than or equal to this. And so you can combine these two inequalities to get something that's kind of like the inequality that you want, and then you have to do a bunch of work to get the inequality that you want. So I'll just quickly say, what does that mean? So the way that I do this is there's a filtration on the ECH of contact manifolds with first Betti number 0 in terms of the linking number with a given orbit. And you can compute that and show that the 2K index generator, so this generator has to have, it has to involve, so you need to have representatives have a minimum linking number with, has to satisfy this inequality. The linking number of representatives of that generator have to satisfy this inequality. By computing this filtration on an example with a standard contact form on this lens space, and then you have to prove that the homology of the complex filtered by linking number with the two binding components of your open book decomposition is invariant of the contact form and depends only on the contact structure. So then you're able to substitute this form for something that's easier to compute with. And then and you need to get the intersection number with the page, so you do that by adding the linking numbers with the two binding components. OK, so I think I'll stop there, and if you have any other questions, feel free to ask me. Thank you.